Okay, let's jump in. Today, we're doing a deep dive into something that sounds maybe a bit specific at first. Rotary positive displacement machines.
Right. Pumps, compressors, that kind of thing.
Exactly. The real workhorse is moving fluids, gases, everywhere from big factories to your air conditioning.
Uh-huh.
And you shared some really interesting material with us, market trends, engineering headaches, and this specific software fix. So our mission today, basically, let's unpack it. We want to get why these machines matter so much financially, really understand the specific simulation nightmares engineers face, and then look at how these specialized tools are, well, promising a solution. Think of it as like a fast track to getting up to speed on this really important, if niche, area.
And important is definitely the word. Rotary PD machines, they're fundamentally different from, say, your standard centrifugal pump. They don't just fling fluid, they trap a specific fixed volume and mechanically push it through. That positive displacement action, that's key.
For high pressure, precise flow stuff.
Exactly, but trapping that volume with rotors spinning super close together, simulating that performance, the flow, the stresses, efficiency, gets incredibly complex. And the markets, depending on them, huge. Just massive.
Yeah, huge doesn't quite cover it based on these numbers you said.
Yeah.
Let's talk money first. The screw compressor market. Forecasted to go from, $16.3 billion up to over $19 billion by 2030.
Wow.
And that's just screw compressors. Then there's the whole positive displacement pump market, pegged at, get this, $27 billion by 2032.
$27 billion. For the pumps alone, that really hits home. These aren't just some obscure parts. They're, fundamental tech powering global infrastructure, manufacturing, energy. When you're playing in markets that big, tiny gains in efficiency or cutting down maintenance, that translates to serious money.
Yeah.
Real competitive edge.
Right. Huge stakes. But the sources also highlight some major pain points in actually developing better versions of these things. What's the holdup? They mentioned rising development costs, just the sheer time it takes for testing, validating designs, getting performance predictions that are actually accurate. And interestingly, designs not being optimized enough to cut down on future maintenance.
Exactly. And you can see how that slows everything down. If you're an engineering team, you're burning more cash, more time, just trying to get a product out the door. If your simulations or tests aren't spot on, you have to build more physical prototypes. Expensive, more tests, more delays.
You're right.
And if you don't design for easier maintenance up front, your customers feel that later, hurts you in the long run. It's this constant fight,
Right.
Time, cost, accuracy.
So this is where digital tools like CFD should come in and save the day, right? The sources mention Computational Fluid Dynamics specifically, vital for predicting performance, guiding design. They immediately call CFD simulation itself a bottleneck today for these exact machines.
It's ironic, isn't it?
Totally. So why? Well, they list the usual suspects, kind of. Need results faster. Finding engineers with the right kind of specific expertise is tough.
Always a challenge.
Poor collaboration between teams. The simulations themselves are computationally heavy. They just take ages.
Eat up resources.
Then there's the manual setup. Apparently, normal measures don't work. It's hungry for time and expensive software licenses.
Yeah.
And the big one maybe, multi-physics.
Oh, yes.
Fluid flow doesn't happen in a vacuum, right?
Yeah.
It affects noise, vibration, NVH acoustics, heat, stress on the parts.
Everything's connected.
And simulating all that together needs even more niche expertise. That's hard to find.
That covers the general CFD headaches many engineers face, sure.
Okay.
But for rotary positive displacement machines, it cranks all those problems up to 11 and adds new ones. The sources really nail down why. First, the geometry itself is just brutal. You've got rotors spinning, the volume inside is constantly changing shape, and the clearances, those tiny gaps between rotors, and the casing, they're critical for performance, but they're microscopic and they're also changing as things rotate. Capturing that movement accurately, huge hurdle number one.
Okay. Tiny moving gaps. Got it.
Then the fluid physics. It's inherently transient, always changing. You might have compressible gases, real gas effects, maybe even cavitation in pumps if the pressure drops low.
Sure.
Complex stuff.
So tricky fluids too.
And you absolutely cannot ignore how the structure reacts. Things heat up, they expand or warp.
Which changes those tiny clearances again.
Precisely. Which changes the flow, which changes the heat. It's a cycle. So simulating the heat transfer, the conjugate heat transfer, or CHT, another layer of complexity. So you combine that constantly morphing geometry, the tiny clearances, the complex transient fluids, and the structural interaction. The sources are blunt. Modeling these accurately with general tools, it takes forever, and the results often aren't good enough. Standard meshing software just wasn't built for these dynamic intermeshing shapes. Or you need these incredibly complex scripts just to get something.
So it takes way too long to get an answer you can actually trust.
Yeah, the bottom line, unacceptably long.
Okay, massive market, tough development, and the core simulation tool is itself a bottleneck because these machines are just so geometrically awkward and physically complex, which leads us very neatly to the solution presented in the source material, twin mesh. From CFX Berlin Software GmbH, it's pitched as a mesher built specifically for these rotary PD machines. And it works with solvers like Simcenter STAR-CCM plus.
Exactly. And the clever part, according to the description, is its core technique, mesh deformation.
Okay, mesh deformation. How does that work?
Well, remember how the geometry keeps changing? Instead of trying to build a totally new mesh grid for every tiny rotation step, which is like computationally insane.
Right.
Twin mesh generates one really high-quality mesh up front, usually hexahedral elements, the sort of cube-like shapes engineers prefer for accuracy. It figures out the mesh for each key rotational position, but the crucial thing is the underlying structure, the topology stays the same.
Ah, okay.
Then, Simcenter STAR-CCM Plus just needs the data on how that single quality mesh morphs or deforms from one step to the next.
Okay, so it's like having one really good stretchy model instead of rebuilding it from scratch every millisecond. That sounds way more efficient.
It should be, yeah. Much less computational overhead.
So what are the claim benefits? Let's tick off those bottlenecks we listed. The sources basically list answers to all those what-ifs, like what if you could achieve better answers quicker? They talk high mesh quality leading to efficient simulation.
Makes sense. Good mesh, good results.
Manageable model sizes,
Yeah.
better accuracy, and this sounds key, no interpolation errors because the mesh connections stay consistent.
Right, that's a big deal for accuracy and transient simulations.
And automation. What if you could automate the workflow? They say it cuts down modeling and simulation time dramatically.
Freeing up engineers to actually engineer.
Which means you can optimize to the right design sooner, reduce simulation costs. It's all about simplify and automate, get answers quicker. They even mentioned democratize simulation, making it more accessible, building the digital twin, using licenses better. There's even a mention of AI potentially automating tasks later. And crucially, simulating the machine and its system together, tackling that multiphysics problem more directly.
Exactly. And you connect that right back to those product development hurdles. Rising costs, time sink, accuracy issues. If you make the core simulation faster, more accurate, more automated, you hit those problems head on.
Less time fighting the software, more time analyzing.
Precisely. More time exploring different designs. Better accuracy means fewer expensive physical prototypes. Finding the best design for efficiency, reliability, whatever, becomes much more feasible when you can iterate quickly. It really aims to change the whole development cycle.
Explore more, improve quality, get it right the first time.
That's the goal, yeah.
Yeah.
Increase the actual performance of the final product.
Okay, so our source material points to how one company, Eaton, is actually finding some real success here. Specifically with their superchargers. These are like classic examples of rotary positive displacement machines, right? Where getting the airflow perfect is everything.
That's right. And the really interesting bit from the source is the specific technical solution they're using. It's not just any old CFD tool. Eaton is successfully tackling these really significant simulation difficulties with their superchargers. You know, specifically those tricky bits around tight clearances and big pressure changes. Using twin mesh for that specialized meshing, that's what's giving them reliable and efficient digital prototyping.
And that digital prototyping is central to how they develop products and predict performance.
Exactly. It's become fundamental for them in this area.
You know, that success really makes you wonder if these advanced digital simulation tools, like this twin mesh and STAR-CCM Plus pairing, are getting so good, so reliable, even for these super complex dynamic problems. What does that mean for the future balance? You know, between virtual testing, simulation, and actual physical prototyping and engineering. And it seems this isn't just for one type of machine. The sources rattle off a whole list. Screw compressors, screw expanders, screw vacuum pumps,
Gear pumps, jar pumps.
lobe blowers, progressive cavity pumps, PCPs, scroll compressors, vane pumps, and more.
That list just shows how common that core challenge is. Simulating that specific kind of moving, tight clearance geometry and the flow inside. Having one specialized tool that handles all those variations efficiently, that's the key value proposition. It lets engineers really understand what's happening inside the transient flow in a compressor, pressure pulses in a gear pump, the weird mechanics of a PCP.
Really interesting. Clearly a very specialized field with unique challenges. Now, if you're listening and this has piqued your interest, the sources you gave us do point towards places to learn more, things like the Twin Mesh website itself. Siemens has blogs on this specific CFD application. There are success stories, even YouTube videos showing it working. So resources are out there.
Okay.
Okay, let's recap the journey then. We started with these huge multi-billion-dollar markets for rotary PD machines.
Vital industry.
Then we dug into the real-world engineering challenges, cost, time, getting accurate predictions. We saw how CFD, the go-to tool, becomes its own bottleneck because of the unique complexities, moving parts, tiny gaps, tricky physics.
The geometry and physics combination, yeah.
And finally, we looked at how a specialized tool, Twin Mesh, with its mesh deformation approach, is positioned as the way to break through that bottleneck, promising faster, more accurate, more automated simulation.
Yeah, I think the main point from the sources is pretty clear. General simulation tools, powerful as they are, kind of struggle with this specific combo of dynamic geometry and complex flow. The standard meshing methods just aren't cut out for it efficiently or accurately enough. So these specialized meshing tools, they're presented as pretty much essential if you want to get high-performance products developed on time in these critical sectors. It's about enabling engineers, really.
So thinking about that, you have this essential, powerful technology, CFD, but it hits a wall with these very specific technical hurdles, like the geometry here.
Yeah.
What does that tell you, our listener, about the value, maybe even the necessity of hyper-specialized tools versus the general-purpose ones when you're really trying to push innovation in a focused area?
Yeah.
Just something to ponder based on what we've discussed today.